Hello everyone, welcome to the 32nd lecture in the series. In this lecture, we are going to cover up another approach for finding the minimal spanning tree given a graph. The algorithm was proposed by Kruskal and we call that as Kruskal's algorithm. With this lecture, we will be seeing what Kruskal's algorithm is, seeing with an example how we could build a minimal spanning tree given a graph using this Kruskal's algorithm, and then we actually look into steps of that algorithm, and finally we will be doing the computational complexity of Kruskal's algorithm. So, by this time you know what a minimal spanning tree is. With the previous lecture itself, we have clearly seen the definition for the minimal spanning tree. So, given a graph G with a set of vertices, the minimal spanning tree is going to be another weighted graph G dash that contains vertices V and E dash such that E dash is a subset of E and G dash is connected, and G dash has the minimal total cost of all the edges. So, G dash is the resultant minimal spanning tree and E dash is the set of edges in that minimal spanning tree. So, this is how Kruskal's algorithm works. Initially our T would be empty spanning tree and E would be the set of edges that are available on that graph, and N is the total number of nodes or vertices available on a graph. While T has fewer than n minus 1 edges, we are going to remove an edge of lowest cost from the edge set capital E, and we are going to check if I add the new edge, that is the edge between the vertex V and W to T, would it create a cycle? If so, then we will be discarding that particular edge. Otherwise, we will add that edge between V comma W to the spanning tree T. So, we will be repeating this process till we cover up or end up in a situation that we have included all the vertices on that graph. So, in order to find the edge with the least cost, we first do a sorting operation on all the edges. We will be sorting all the edges based on the weights assigned to those edges, and we will be processing the edges one after the other according to the weights associated with them. And also we have to be very sure that the resultant by adding an edge to the spanning tree, it should not yield up in a situation that we enter into a cycle. In order to avoid getting into cycles, we use another algorithm named union and find. So, it is just to check whether we are picking up an edge from two disconnected components. So, if suppose we end up, we pick up an edge from within a connected component, then there is more probability of entering into a cycle, and this operation is mainly to check whether we do not pick up an edge that lies within the same connected component. So, if suppose both the nodes V and W are in the same component of the tree, then we adding the edge between V comma W would probably result in a cycle, and so we try to avoid that with this algorithm. Of course, we are not going to focus much on this algorithm. Of course, we will be seeing how it actually works while solving the problem. So, this is the actual Kruskal's algorithm. Initially, we have sorted up all the edges in this graph G in increasing weight order, and the resultant is being stored in the vector EG, and E is initially empty. So, E marks up the edges that are going to be part of the minimal spanning tree, and initially we have initialized the variable I to 1, which is the counter for EG, and while E is less than n minus 1, we do this set of steps again and again. We will check if adding an edge from EG to E, does it result in a cycle or not. If so, we do not think of adding that edge to that tree, we will simply discard it. If not, we will be adding that edge to the edge set EG, and then we increment I by 1 and we will repeat this process. And so, this Kruskal's algorithm, we call it as a greedy approach just because we do not stop at a point that we have found out a solution, rather we still try during every iteration, is there a way to find some other alternate way to reach a vertex with the least cost. So, when you talk of complexity of this particular algorithm, this algorithm runs at a complexity of E log E times. And let us consider an example of to see how this Kruskal's algorithm works. You are given with the undirected and weighted graph, and as such the Kruskal's algorithm initially builds a forest. So, as such, since this graph contains 6 vertices, we have 6 different trees, and that makes up the forest. And edges, we assume that in order to pick up the edge with the least cost, we have a heap being implemented, and we, for simplicity sake, that heap is not shown here, but we assume that we have a heap, and every time the heap gives the minimal I mean the edge with the minimal weight every time we do a delete min operation. So, here given this graph, you could see that we have taken this particular edge, that is the edge between 2 and 3 as the one with the least for the first time. So, that is the edge with the least cost that has been picked, and as such we do a find operation. So, you know that we are going to do a find and union operation. So, the purpose of find operation is to check what are all the components that are connected to that particular vertex. As such, initially, as you see, we started with having a forest, right. So, the vertex 2 was a separate tree, vertex 5 was a separate tree. So, find of 2 will yield 2, find of 5 will also yield only 5, and when I take a union of 2 comma 5, then that is going to be this edge. So, as such that is what we have done. From now our forest has been, this is the resultant forest, we have 1, 3, 4, 6 as separate vertices, whereas 2 and 5 have been grouped together by this union operation. As such, one edge has been accepted at this point of time. Now, we continue with the next step. So, in the next step, we again choose the edge with the least cost. So, we assume, I mean we have chosen the edge between the vertices 2 and 6, and we do a find operation of 2. So, now this find operation of 2 will have 2 alone, and find operation of 6 will have 6 alone, and we take a union of 2 and 6, and so all these have been linked up. So, now we have one component including 3 vertices and 2 edges. So, here now the resultant forest would be 1, and 2, 5, 6 is a connected component, and 3 and 4 are separate trees. So, as such, by this time we have accepted 2 edges to be part of this minimal spanning tree. Next is we have to select an edge with the least cost, and so we pick up the edge that is between the vertices 1 and 3. So, as such we do find operation between 1 and 3 again, and find of 1 is 1 and find of 3 is 3, and now we take an union of 1 and 3. So, as such this edge has been accepted. So, now the resultant forest would be 1 and 3 as one tree, 2, 5, 6 is another tree, and 4 is a separate tree. As such, three trees make up this forest. And next is we have to pick up the other edge with the least cost. So, our possible choice is the edge with the weight of 2, that is between 6 and 5. And as you know, if I add this edge, we will enter up into a cycle. So, we have to avoid it. So, for doing so, what we do is that we do a find operation of 5. So, find operation of 5 results in a value of 2 just because 2 is its parent, right. 2 and we do a find operation on 6, that also yields its parent, which is 2, because initially there was 2, and to 2 we have connected 5 first time, and with 2 we connected 6 the second time, and so for both of them the parent is 2. And so, when you do an union, you could see that both of them are 2, and so we do not take up this particular edge, rather we discard that edge. And then so during this iteration none of the edges have been accepted, and so we remain in this step with just 3 edges accepted. Now, we move to the next iteration, wherein we pick up the next edge with the least cost, and probably the next edge with the least cost should be 4, right. And so, we have chosen the edge between vertices 3 and 4, So, we have one edge with the least cost 3 here. So, we are just taking it up instead of this. So, we have the edge between vertices 3 and 4 as 3. So, we have taken that. We do a find operation on 3. For 3 its parent is 1 because 3 was attached to 1 before, and for 4 operation so far it is a independent tree, and so for find of 4 it would return 4. Now, we take a union of 4 1 and 4. So, that would yield us adding this new edge to this tree. So, one this edge and this edge now part of the same this becomes a connected component, vertices 1 3 and 4 they become another connected component. Now, that you could see that the resultant forest has been reduced to 2 trees, one with vertices 1 3 4 and other with vertices 2 and 5, and by this time we have accepted 4 edges to be part of the minimal spanning tree. At the next step we are supposed to find the next edge with the least cost, and our choice is the edge between vertices 4 and 5. And so, you do a find of 4, find of 4 would result in its parent which is 1, find of 5 would result in its parent which is 2. So, as such they are part of 2 different components, and so we can very well add this particular edge to the minimal spanning tree. So, upon adding this tree the entire forest got reduced to a single tree with 6 vertices, all the 6 vertices have now been included, and as such by this time we have accepted 5 edges, and the total cost we are supposed to sum up the weights associated with all those edges we have accepted, and so the total cost is 10 here. And so, this is going to be the end of this Kruskal's algorithm. So, here Kruskal's algorithm always makes an attempt to avoid cycles. So, to do that it sorts the edges by their weight, and it tries to build a spanning tree from a forest, and eventually it converts that to a tree, and every time it adds the edges with the minimal cost as we saw with the previous example, and every time we add an edge to the tree we just make a check whether including that edge will make the tree to form a cycle or not, and we keep on doing this till we bring in all the vertices of that graph into a tree. So, we are going to see one more example here. So, here in this case we have chosen vertex 5 as the start vertex, and from there we have chosen this edge as the first edge in the minimal spanning tree because it is the edge with the least cost from among the set of edges that you find here. So, from among the edges we have picked up an edge with the least weight which is 23 in this case, and next we have to look at the next edge with the minimal weight. In our case it should be, we have an edge with cost of 29 here. So, that should be the next choice, and after that the next edge should be 31, and followed by that we may have to pick up 32. So, we have picked up 31 and then picked up 32, and then we have to look for next possibility. So, here we have 147, and other than that everything is greater than 47. So, we may have to choose that. Then we pick up this 54, right. So, before that, and then the next possibility should be 55, but as you see here if I include this 55 there will be a cycle, and so I should not add this particular edge to that graph. Then I should look at the other possibility which should be, I think from this graph it should be 66 here with the minimal weight, and so it should be picked up. So, up to this particular point we have simply taken up the edges in the order of their weight, but at this particular point we, as I said before, we are rejecting a particular edge just because if we add that edge it will form a cycle for us, and so we are just discarding this edge and we are moving ahead in finding the next edge with the minimal weight. So, thereby we are able to find this particular edge, and so by this time you could see that we have marked all the vertices as visited, and so we say that we have ended up with the minimal spanning tree. Now, we are supposed to find the total cost associated with the minimal spanning tree, which is summing up the weights associated with all those edges that we have chosen, and the resultant weight is 282 in this particular case. So, we have one more example which is a complicated graph. You could see that the graph contains some too many vertices and multiple edges between every pair of vertices. And in this case also with Kruskal's algorithm every time we pick up the edge with the least weight. So, first of all we sort all the edges according to their weights and we have chosen the one with the minimal weight. So, in our case we have chosen this. In the next iteration we are supposed to choose this particular edge with the cast of 184, and after that we picked up the edge with the cast of 187, and from among the remaining available possibilities the next one available is 337, and after that we have something around 600 here, and then something around 700 here, and then with 800 we have two possibilities, of which we will be picking up one with the least cast. So, here we are choosing 621 here. As such, by this time you could see that with Kruskal's algorithm we started with the forest, which means all the vertices would be treated as separate trees. As such, you see here some 9 vertices and all of them would be separate trees. At this moment we have just ended up with say this becomes one tree, this becomes another tree. So, 5 vertices here and 2 vertices here. So, these two have become two connected components, and other than that we have two separate trees which are the vertices that have not yet been marked as visited. And now the next vertex available with us is, I mean the next edge with the least weight available with us is with 740. But if you think of adding the 740, then what happens is that it will end up in a cycle, and of course you know that all these two vertices have already been visited through some other edge, and so we just discard this edge, and then we may have to pick up another edge here at a cast of 802. So, upon adding this edge, what happens is we have added up a new vertex onto that graph, onto the spanning tree, and as such there is one more vertex yet to be visited at this point of time. And our next possibility is to pick up the next edge with the least cast, which is 849 in this case, and we do not add this particular edge here, because if we add the particular edge to the minimal spanning tree, then there is a possibility of entering into a cycle. So, we just discard this edge. Then we have to choose the other edge with the least cast. In our case it is 867. If we add that, then also there is a possibility of entering into a cycle, and so we just discard that edge. And the next possibility is including 946 here, and we add that to that minimal spanning tree, and by the time you could see that we have got two forest has been reduced to 2 trees, and only thing is we have to establish connection between this component and the other component here. And our next possibility is to find some edge with the cast greater than 946, and probably the next one should be 1090. But if we add this particular edge, then what happens is there is a possibility of entering into a cycle again, and so we discard this particular edge. And the other possibility is having this particular edge, then also there is a chance of entering into a cycle. So, this edge is discarded, and finally we are picking up this edge with the least cast, which is 1235. So, upon adding this, you could see that we have connected all the vertices in that graph, and then now we have found a spanning tree. And next is that we stop at this point of time, as we have visited all the vertices in this particular graph and we have got a resultant tree, and the total cost of the spanning tree would be the cost of all the edges that we have chosen to be part of the minimal spanning tree. So, here when we do analysis of this Kruskal's algorithm, initially we started the algorithm by having a forest. So, as such whatever number of vertices the graph had, all those vertices are treated as independent trees. So, if there are n vertices in that graph, we initialize actually n number of forests, and so it takes up a time of order of n. And then for finding the edge with the minimal weight, we are going to have a heap implemented, and for that we are going to take up a time of order of m, where m is the set of edges that you have, and then we may have to iterate upon m number of times for doing this operation. First is that in order to fetch the edge with the minimal weight, I have to do a delete min operation on the heap, for which I may take up a time of order of log m, and then I have to do a find and union operation. The purpose of find and union operation is to discard any probability of entering into cycle, and every time a new vertex is being added, we just every time we find an edge with the minimal cost, an edge is associated with the pair of vertices, and for both the pair of for both the vertices we will be doing a find operation, and each of those find operation takes up an order of log n time, and then we do an union operation to decide whether it leads to a cycle or not. So, for that we check whether both the vertices are part of the same connected component or not. So, for doing that union operation we need an order of 1, it takes up a constant time, right. And so, the worst case complexity of this Kruskal's algorithm would be order of m log m, or order of m into log n. So, here when we again when we are talking about time complexity, when we are comparing the time complexity of Kruskal's algorithm with that of the Prim's algorithm that we learned before, with Kruskal's algorithm we started with having a forest, and then gradually that forest gets converted into a tree. So, every time we sort up all the edges on that graph according to their weights, we add one after the edges to that tree one after the other in such a way that adding that edge does not lead us to a cycle. So, if suppose we have a graph with v vertices and e edges, then the Kruskal's algorithm is supposed to take a time of e log e, whereas the Prim's algorithm takes up a time of e log v. So, in short, to make up to arrive at a conclusion of when to use Prim's algorithm and when to use Kruskal's algorithm, if suppose your graph is a sparse graph, then in that case Kruskal's algorithm is preferable. So, for instance, we call a graph as sparse graph provided the edges between a pair of vertices is less when compared to the total number of edges. So, for a sparse graph, Kruskal's algorithm is the best choice, and for dense graph it is better that we use the Prim's algorithm to find the minimal spanning tree. So, to summarize what we have seen so far, Kruskal's algorithm can be used to find the minimal spanning tree given the graph is connected, it is weighted, and it is undirected. And when we say that it is a weighted graph, the weights are all should be non-negative. And the objective of Kruskal's algorithm is to give a spanning tree, and that spanning tree's total edge weight should be as minimal as possible. Just like Prim's algorithm that we learned before, it also makes use of the greedy approach. It first sorts all the edges by their weight and then add it one after the other to the minimal spanning tree so as to avoid cycles. Hope by this time we learnt two properties that are used in minimal spanning tree, one called as cycle property and another one called as cut property. The cycle property is primarily used by Prim's algorithm, whereas the cut property is primarily used by Kruskal's algorithm. So, with cut property what we say is that every time we add an edge, we pick up an edge with the minimal cost and we assume that the edge actually connects to disconnected components, and so its presence is quite unavoidable in the minimal spanning tree, because if we do not include that edge, then ultimately the graph would become disconnected, and so we very well accommodate such an edge into a minimal spanning tree with the fact that that edge is very mandatory for retaining connectivity, and it should be the one with the least cost. It can never be avoided. So, such an edge is given top priority with cut priority, and this Kruskal's algorithm always proceeds with choosing the edges by following the cut property. And for cycle detection, we use this concept from disjoint set union or union find operation, and that helps us to efficiently check whether adding an edge will take us to a situation of a cycle or not. And then we have analyzed the complexity of Kruskal's algorithm, and we learned that it runs at the time of order of e log e, and this time is mainly due to sorting up of edges in order to pick up an edge with the least cost. And when you look at the growth in terms of edge, unlike prims, it does not grow from a starting node, whereas here we build the minimal spanning tree by connecting components. We started with the forest and then we grouped together trees, and then we proceeded with finding connected components, and ultimately finally we merge all the connected components to build that minimal spanning tree. And when you talk of applications, Kruskal approach is mainly used for sparse graphs and in network designing, and mainly for clustering as well as for circuit design problems. Hope you are now thorough with the concept of Prim's and Kruskal's algorithm for finding the minimal spanning tree, and we will be seeing the rest of the concepts with the next few lectures, and thank you.